We will start Unit 3 with a discussion on work done by a force. When does a force do work? Do all forces do work? Well, no, not all forces do work. You can see I am actually applying a force to hold this in place. But this force is not doing any work. But when I lift it up, I am applying a force and making that force move. Only when a force moves or produces displacement will that force do work. Work is done by a force when it produces a displacement. A force that does not produce displacement will not do any work. Now, very often in our normal language, we distinguish between work and play. Is that right? You know, little children sing work while you work and play while you play. Well, isn't playing working? You hit a tennis ball with a racket. You can see you apply a force and move that force. You're working. The moment you jump up to shoot a ball, when you jump up, you are moving a force equal to your weight. So when I jump up, I'm doing work. So in physics, there is no distinction between working and playing. Whenever a force produces displacement, that force does work. And how do you measure work? Work done by a force is measured as the product of the force and the displacement it produces in the direction of the force. It is very important. If there is no displacement in the direction of the force, then there will be no work done. You remember we did a problem in the last unit. What is the work done by the force of gravity on the moon? The force of gravity does not produce a displacement in the direction in which it is acting. Therefore, it does no work. So work is done only when the force produces a displacement in the direction of that force. Now let's consider a force F applied on a box that is kept on a surface. A force F that is applied on a box produces a displacement. Let's move that box and it comes over here. What is the displacement? The displacement is x. Therefore, what is the work done? Work done is a measure of force multiplied by displacement in the direction of the force. So work equal to F Newton multiplied by x meter. Force multiplied by displacement. That will be F times x Newton meter. The unit of work is a Newton meter and we call that unit a joule. And we write it using the uppercase J. So what is the unit for measuring work? Work is measured in joules and it is a Newton meter. When 1 Newton force produces a displacement by 1 meter, the work done is 1 joule. Now, what happens if the displacement is not exactly in the direction of the force? Now, if you look here, I have a force F that is at an angle theta with the horizontal. And if this force produces a displacement along the horizontal direction, what will be the work done? Will there be any work done? Well, Here, work is done by the component of this force in the direction of motion. Alright, tell me, what is the component of this F in the direction of motion? Well, once you know that, you can calculate the work done. Well, the component of the force in the direction of displacement is the horizontal component of the force, and that will be F cos theta. That means, although there is a force F there, not all that force is doing work. Only the horizontal component of that force produces displacement in the direction of that force. That means only F cos theta does useful work. Therefore, work done in this case will be the F cos theta produces a displacement x. So if the box is now displaced through a distance x, this displacement is produced by this component F cos theta. Therefore, work done will be F cos theta Newton multiplied by x meter. That will be Fx cos theta joules. Is that right? The big J stands for joules. So work done is the product of the component of the force in the direction of displacement and the displacement multiplied. The work done W is F cos theta multiplied by x. Alright? Work is the product of force and the displacement in the direction of motion. Or work is the product of displacement and the force in the direction of displacement. Well, and work done is measured in a unit called joules, which is a Newton meter. The work done by a force can be better understood by studying the dot product of two vectors. Now, we have actually seen how to add vectors. We haven't seen how to multiply vectors yet. Vectors can be multiplied in two distinct ways. We will now look at the meaning of dot product of two vectors. Now look at two vectors, a vector A and a vector B makes an angle theta. The component of vector B in the direction of vector A is B cos theta. Is that right? That means B cos theta and vector A are in the same direction. So, if A and B are two vectors and the angle between them is theta, then the component of B in the direction of A is B cos theta. Now, if you understand that, we can now use this to define the dot product of vectors A and B. And this is how you define the dot product. The product of vector A and the component of B in the direction of A is called the dot product of the two vectors. And we will write it like this: A dot B. That's the way you read it. A dot B. So what is A dot B? A dot B is the product of vector A and the component of B in the direction of vector A. So that will be A times B cos theta. And that is not a vector quantity. You see, A dot B is not a vector quantity. It has just a magnitude. So how do you find the magnitude of this? Multiply the magnitude of A with the magnitude of B in the direction of A. Now this is the way we write magnitude. You see that? We write them in between two lines on the left and two vertical lines on the right, and you read it as norm A. Norm, N-O-R-M. It means the magnitude of A. So A dot B is the magnitude of A times the magnitude of B times cosine of the angle between them. And A dot B is not a vector, it is a scalar quantity. And for that reason, the dot product of two vectors is also called the scalar product of two vectors. So A dot B is a scalar quantity, and its value is the magnitude of vector A multiplied by the magnitude of vector B multiplied by the cosine of the angle between the two vectors. Now that helps us to solve for cos theta. Cos theta equal to A dot B divided by magnitude of vector A times the magnitude of vector B, and that will help us to find that angle theta. Theta equal to cos inverse of A dot B divided by magnitude of A times magnitude of B. Well, there is a very quick way to find the dot product of two vectors once the vectors are given in the component form. For example, let me show you one quickly. If I have a vector A is 4i plus 2j, and vector B is 2i minus 3j. A dot B, remember A dot B is a scalar quantity. Now what you need to do is multiply the x components. 4 times 2 is 8. Now when you multiply, you don't use the i's anymore. Remember, i's and j's are used only for vectors. If a quantity is not a vector, then there is no need for I and j. So multiply the x components. 4 times 2, 8. And then multiply the y components. 2 times negative 3 is negative 6. And simply add them together. So A dot B is 4 times 2, 8 minus 2 times 3. So that will be 2. A dot B has a value 2. Again, A dot B is a scalar quantity. It has only magnitude. So whenever vectors are given in the component form, the dot product can be simply found by multiplying the x components, multiplying the y components, and adding them together. Now watch here, when you multiply the x components, the i's will not come with it. Why? Because the dot product is not a vector. Let's do a problem. If vector A and B represented in the component form, then the dot product of the two vectors is obtained by adding the product of the x components to the product of the y components. Let's do one quickly. A equal to 2i minus 3j, B equal to 5i plus j. What is A dot B? A dot B is, multiply the x components. 5 times 2 is 10. Negative 3 times 1 is negative 3. 10 minus 3 equal to 7. A dot B equal to 7. Well, remember again, it has only magnitude. Now, once you understand the meaning of dot product of two vectors, it is easy to understand that work done by a force is actually the dot product of the force vector and the displacement vector. If you notice here, a force vector F produces a displacement S on this object. F is a vector, S is a vector. Now what is work done? Work done is the product of the displacement vector and the component of the force in the direction of that displacement. Now the component of the force in the direction of displacement is F cos phi, where phi is the angle the force makes with the direction of displacement. And therefore work done is F dot S. What does that mean? It means it is S times the component of F in the direction of S. It is F times S cos phi. That means work done by a force is the dot product of the force vector and the displacement vector. It is the product of the displacement and the component of the force in the direction of displacement. That's what it means. Alright. Work done is a measure of the dot product of the force vector and the displacement vector. In other words, W equal to F dot S. Now here, S is the displacement vector and F is the force vector, and therefore F dot S equal to F times S times cos theta. The magnitude of force vector times the magnitude of the displacement vector times cosine of the angle between the two vectors. And theta can actually be then written as, can you write an expression for theta? We had written that earlier. Theta will be cos inverse of F dot S divided by magnitude of F times magnitude of S. Cos theta equal to F dot S divided by F times S. And therefore theta is cos inverse of that quantity. Let's do a small problem. Find A dot B and the angle between A and B if vector A is 4i plus 6j and vector B is negative 2i plus 3j. Also find the angle between vectors A and B. Well, the first thing to do is to find the dot product of vectors A and B. How do you find the dot product of vectors A and B? Multiply the x components. Now 4 multiplied by negative 2 is negative 8. And multiply the y components. 6 multiplied by 3 is 18. So A dot B is negative 8 plus 18. That is 10. Okay, now tell me, what is the magnitude of this vector A? Vector A is 4i plus 6j. What is the magnitude of that? Well, magnitude of a vector is the length of the vector. 4i plus 6j is this vector, 4i plus 6j, and the magnitude is the length of this. Now this is 4, this is 6, therefore the magnitude of the vector A will be square root of 4 squared plus 6 squared. Is that right? So vector A is 4i plus 6j. Its magnitude is the length of that vector, which is square root of x squared plus y squared. Alright? So magnitude of A is square root of 4 squared plus 6 squared equal to 7.2 approximately. And magnitude of B is negative 2 squared plus 3 squared, and that is approximately 3.6. Alright, what is the work done? Well, we have already found the work done, is that right? Because work done is a measure of the dot product of the two vectors. But I don't think I wrote it correctly. I should have written one more step there, and like this. Because A dot B equal to 10, work done therefore equal to A dot B equal to 10 joules. Then only that answer will become complete. Work done by the force therefore is A dot B. Well, apparently we are not asked to find the work done. We are asked to find only A dot B. Well, cos theta equal to A dot B divided by magnitude of A times magnitude of B. And what is that equal to? A dot B is 10, and you know these values. That will be 10 divided by 7.2 times 3.6. That is 0.386. Therefore, theta equal to cos inverse of that value, and that is 67 degrees. Rather simple type of problems. Another problem. A force vector F equal to 5i minus 2j acting at a point produces a displacement given by S equal to 3i minus 4j. Find the work done and the angle between the two vectors. The same problem, the one we did before. So, since the work done is a scalar quantity, the dot product of the vectors is a scalar quantity, and for this reason I told you the dot product is also called the scalar product of two vectors. And you know how to find the dot product. F equal to 5i minus 2j and S equal to 3i minus 4j. What is F dot S equal to? Multiply the x component, multiply the y components, and add them together. So the product of the x component is 5 times 3, 15. And the product of the y components, negative 2 multiplied by negative 4 is 8. Therefore, the work done equal to F dot S equal to 15 plus 8, that is 23 joules. Alright, now we need to find the angle between the two vectors. What do you do for that? Well, first of all, we need to find the magnitudes of these vectors. What is the magnitude of the force vector? It will be square root of 5 squared plus 2 squared. You don't need the negative sign because when you square it, it becomes positive. And that will be square root 29. The magnitude of the displacement vector is S equal to square root of 3 squared plus 4 squared, that is 5. Angle theta is cos theta equal to F dot S divided by magnitude of F times magnitude of S. That will be 23 divided by square root 29 times 5. And that is 0.854. Therefore, theta equal to cos inverse of 0.854. And do that on your own and see what you get. Cos inverse of 0.854 is 31.4 degrees. So the work done we calculated as 23 joules. That is the work done. And the angle between the two vectors is 31.4 degrees. Let's now do another problem. A 3 kilogram block slides down a frictionless plane inclined 20 degrees to the horizontal. if the length of the plane is 1.5 meter and the coefficient of kinetic friction between the block and the plane is 0.275, calculate the net work done. Now tell me, if an object is sliding down an inclined plane, what are the forces that will do work? Well, when the object is sliding down the inclined plane, there are actually two forces involved in there. Is that right? As the block slides down the inclined plane, the component of the force pulling the object down the plane, what is that component? mg sine theta. Well, that does work, and the frictional force is acting up the plane, and that force also does work. If one work is positive, the other work will be negative. Now remember, work done is not a vector quantity, but if the work done by a force acting in this direction can be considered positive, the work done by a force in the opposite direction will be considered negative. So in this case, work is done by two forces, and we are required to find the net work done. Now here is the object sliding down the inclined plane. When the block slides down the inclined plane, the frictional force acts up the plane. Now, do you remember the equation for the frictional force? The frictional force is mu times Fn, the normal force. And the normal force in this case is mg cos theta. Therefore, the force of kinetic friction. Why is this the force of kinetic friction? Because the object is sliding down the plane. The force of kinetic friction is mu k mg cos theta. Now the force of kinetic friction between the block and the plane is Fk equal to mu k mg cos theta. And that will be mu k is given 0.275, m is 3 kilogram, g we know, and the angle is 20 degrees, so that will be 7.6 Newton. The frictional force acting up the plane is 7.6 Newton. Alright, there I have a frictional force is 7.6 Newton. The force F pulling the block down the plane is mg sine theta. M is 3 kilogram times g times sine of the angle, and that will be 10.1 Newton. So the force pulling down the plane is 10.1 Newton. Alright, if the work done by the force pulling the block down the plane is positive, then the work done by the friction acting up the plane is negative. That concept we'll be using as we go on. If work done by a force in the positive direction is positive, the work done by a force in the negative direction will then be negative. So, work done by the force pulling the box down the plane is the force down the plane, that is 10.1 Newton, times the displacement. Now, what is the displacement? The object is going to slide down the entire length of the plane. And we are told that the length of the plane is 1.5 meter. So, force multiplied by displacement in the direction of that force, and that will be 15.15 joules. What is the work done by the frictional force? It will be negative 7.6. Because we use 10.1 positive, we will use 7.6 negative. Negative 7.6 Newton multiplied by the same displacement. Displacement is the same in both cases. That will be negative 11.4 joules. And so what is the net work done? The net work done is 15.15 minus 11.4, that is 3.75 joules. And that is a measure of the net work done in that case. Okay, another problem. A father pulls his young daughter on a sled with a constant velocity on a level surface through a distance of 10 meters. If the total mass of the sled and the girl is 35 kilograms and the coefficient of kinetic friction between the sled runners and the snow is 0.25, how much work does the father do? If the force applied makes an angle of 30 degrees with the horizontal. Well, once you picture that problem, it actually becomes simple. We don't know the force applied by the father on the sled. So we may have to figure that out first before we can find out the work done. Is that right? Okay. Now, if you want to picture this problem, here is the sled and this is the snow, and the father is pulling the sled like this at an angle. We know the angle. Now tell me, what are the two forces here? Well, this force makes an angle theta with the horizontal. It has a horizontal component F cos theta, and that F cos theta is the force that does useful work. And it has a vertical component F sin theta. Tell me, what does that F sin theta do here? Now, when you want to measure the frictional force between the two surfaces, what is the equation for the frictional force? Well, the frictional force, the frictional force will be Fk equal to mu k Fn. Is that right? The frictional force Fk equal to mu k Fn. Fn is the normal force. That means when the father pulls the child with a force like this, the vertical component of this force actually reduces the normal force. You see, the normal force is the force that is pressing the sled onto the surface. Now, the force that is acting down the plane is mg, is that right? That is pressing the two together. And when the father pulls the sled like this, the component F sin theta is up the plane like this. That means the normal force Fn is now mg minus F sin theta. So there is an advantage in pulling the child like this rather than pulling it horizontal. What is the advantage? By providing a normal component of this force, we are reducing this normal force that presses the two surfaces together, thereby reducing the frictional force. Alright? We will be using this concept to solve this problem. So you must understand that concept well. Okay. Let's now draw a diagram. Here is the sled. Well, it's a very cute sled though. The sled is pulled with a constant velocity. What does that mean? It is pulled with a constant velocity. There is no net force on the sled. Now, the weight of the sled and the child is, the total mass is given to be 35 kilograms. Therefore, the weight is mg 35 kilogram times 9.8 meter per second squared is 343 Newton, which will be acting down the plane, and that is the force that presses the sled and the child to the snow. The force F applied by the father makes an angle 30 degrees with the direction of displacement. So F makes an angle 30 degrees with the direction of displacement. What does that mean? It means the component of this force in the direction of displacement is F cos 30 degrees. Now, using the value of cos 30 degrees, that will be 0.87 F. That is the force that is actually acting in the direction of displacement. F cos 30 degrees is 0.7 F. And the component of F at right angles to the displacement is F sine 30 degrees, that is 0.5 F. This is the normal component or the vertical component of this force, that will be 0.5 F. The net force pressing the sled to the floor, therefore the net force pressing the sled to the floor is 343 minus 0.5 F, and this is a measure of the normal force between the sled and the ice. And therefore Fn equal to 343 minus 0.5 F. The force of kinetic friction Fk acts opposite to the displacement, is that right? Force of kinetic, if the displacement is to the right, the force of kinetic friction is to the left. And what is the equation for that force? Fk equal to mu k Fn. Mu k is given to be 0.25 and Fn is 343 minus 0.5 F. Well, we have said earlier that the forces on the sled are balanced because the sled is being pulled by a constant velocity. What that means is the Fk acting to the left, this Fk, which is mu k Fn, given by this quantity, is exactly equal to 0.87 F. You see that? Now, if you can now take these two and equate them, we can calculate that F. That is a strategy of this problem. So once again, when the sled is pulled with a constant velocity, the net force on it is 0. That means the force acting to the right, 0.87 F, minus the force acting to the left, which is mu k Fn, and which is this quantity, that must be equal to 0, or this quantity 0.87 F must be equal to the frictional force. Now, since there is no net force on the sled, 0.87 F Newton pulling the sled forward is balanced by Fk, which is this quantity. So I can now take this quantity Fk and set it equal to 0.87 F, and you can see we got an equation that contains only one variable, that is F. Solve for F, distribute and combine the terms in F and solve. You get F equal to 86.2 Newton. The force applied by the father is now 86.2 Newton. We can now find the work done. The displacement is 10 meter. Therefore, what is the work done? The work done is, work is done by this force, 0.87 F. F cos 30 degrees multiplied by the displacement. that is 0.87 F multiplied by 10, and that will be 0.87 times F equal to 86.2 Newton. The displacement is 10 meter, and therefore the work done by the father is 750 joules. Now this is a good problem, and it's good to know the method of solving problems like this.